Memory management boils down to a question of malloc and free, and we've looked at simple programs that use malloc and free directly, but realistic programs often use malloc and free indirectly, such as functions that read a list of names from a database, or functions that create graphical widgets in a graphical interface. And when you have larger programs using these kinds of libraries, often the allocation questions are not as obvious. Malloc and free underneath work the same, but the question is who is calling malloc and free, and what function do you call to allocate? For example, when we get a list of students from the database, this is an array of char stars, an array of strings. How do we free that? Is there a function to free it? And if we send those names to the listbox widget to set its list of choices, does the listbox break if we free the names? Is the listbox responsible for freeing the names? Does it make a copy? And so on. Another issue here is we created the listbox and maybe we want to use it for a while, but after we install this listbox into some window that implements a directory, does the window take it over? Can we still refer to it? What happens if we close the window, and so on? So all of these things are issues that show up in the API of a C library, and you just have to follow the rules in general. Another strategy for taking care of this is automatic memory management. Since the difficulty is when to call free, make the problem of figuring out when to call free someone else's problem. Have the language provide that for you. As usual, we will boil this problem down to a simple kind of example so that we can look at it. And so we'll consider today just allocating nodes in a binary tree. And we won't even bother with data in the binary tree. We'll just have nodes that have a left node and a right node. Of course, the interesting part is that an allocated node has other allocated things in it for this left and right. And as just a program to exercise our node allocator, then we'll use this makeTree function, which builds up a tree of the given depth, but also makes some intermediate trees along the way and destroys them to simulate some useful things that a program might do in allocating temporary data. Now, if this makeTree were in a library to be used by C programs, in addition to makeTree, we would need to provide some sort of deallocator. So that's destroyTree here. And you can see what destroyTree does is take the tree and goes and deallocates everything in the tree. So this is great for a program that wants to create one tree and destroy one tree, but what if the program creates a tree and wants to grab a piece of that tree and keep that but destroy the rest? It doesn't really fit into this API, and the kinds of more automatic memory management tools that we want to look for would make that easier and simulates the way that we want to make that kind of task easier in real programs. So what we would like to write in some language, maybe not necessarily C, is something that looks more like this. So when you call makeTree and it does some simulation of a work here, it can make a tree. It doesn't have to explicitly destroy that tree. The automatic memory management is supposed to take care of that somehow. And so just to make it clear, we could provide a destroy tree function, but we're just going to make it do nothing because the automatic memory management layer is supposed to take care of releasing nodes that aren't going to be used. So I put a blue background in this box to say this is a kind of program that we want to write directly, but of course if we want to do this in C, there might need to be some sort of transformation of this code to make the memory management explicit to the C compiler and runtime. As we look at different possibilities for memory management, we'll consider two main possibilities: reference counting and garbage collection. The idea of reference counting is you keep track of how many times a particular object is referenced, and when that number of times goes down to 0, then the object gets freed. And so the timing that the free call, the implicit call to free in the program, is predictable based on when that object stops being used. That means the overall memory use of reference counting is going to be similar to the overall memory use of manual calling free manually. But we'll see a big drawback of reference counting, which is that it doesn't handle cyclic references among objects that are allocated. Garbage collection, on the other hand, does handle cyclic reference, but the strategy for doing this relies on delaying the free almost indefinitely until it really has to be done, and so the timing, exactly when free gets called, is less clear to the programmer. For many applications, that's just fine. You don't care when free is called as long as it's called eventually. On the other hand, it does mean that the footprint tends to be larger. More memory tends to be used overall. Lower utilization, in other words. We're going to look in detail at these two approaches to automatic memory management.